Okay, welcome to lecture here. We're continuing on with the never ending chapter 14. Okay, so last time we pretty much kind of finished up talking about buffers. Again, a buffer is a solution that's able to resist changes in pH, even when you add acid or base to it. Remember, as we talked about, a buffer is not necessarily a neutral solution. You can make a buffer at any pH that you want. But basically, what it means is, again, once it's at that pH and you add either some acid to it or some base to it, it's usually able to maintain its pH. And it's able to do that because, again, a buffer contains a weak acid and the salt of its conjugate base, are a weak base and the salt of its conjugate acid. And ultimately, as we talked about last time, what a buffer pretty much has in it is an acid part, really, and a base part. So when you add additional acid, the base part of the buffer will react with it. And ultimately, what it does, as we talked about last time, is prevent the formation of free H plus from floating around in that solution. Because it's able to prevent any more free H plus from going into that solution, it pretty much keeps that concentration constant. And since pH is basically related to the amount of H plus that's in that solution, it keeps the pH relatively constant as well. Same thing happens if you add a base to a buffer, the acid part of the buffer will react with it. And ultimately, what it's doing is preventing the formation of free OH minus or hydroxide ions in solution. And that's important because, as we've talked about previously, hydroxide and H plus concentrations, they're related to each other. So as one goes up, the other goes down. So by preventing more hydroxide from going into the solution, what it's able to do is essentially maintain the H plus concentration. And again, the pH remains relatively constant. Again, I say relatively constant because, as we saw in some examples, and as you would see if you kind of stuck a pH meter into a solution and we're monitoring the pH, if you added some acid to the buffer, you would see the pH go down. So what we're talking about, sort of maintaining the pH, is not a tremendous big giant jump in the pH. So again, if the pH of the buffer was 5 and you added some acid, maybe it goes down to 4.9, somewhere in that ballpark. It's not going to go from 5 all the way down to, say, a pH of 1, that tremendous jump in pH, again, because it's pretty much able to maintain the H plus concentration. Now, really, buffers are nothing more than common ion type problems. And that's because in order to make a buffer, you have a weak acid or a weak base and their conjugate partner. So they're pretty much going to always have that common ion effect. And pretty much we use the Henderson-Hasselbalch equation, like we talked about last time, as the really equation referred to be used as a buffer equation, really. So that's really sort of the formula that we use for a buffer. So if you're just looking to calculate the pH of a buffer, you pretty much could go right into the Henderson-Hasselbalch equation, which is that pKa plus the log of the base over the acid. To calculate the pKa value, you take minus the log of the Ka. And you could go right into it. We also talked about an alternative to that is you could still do an ice table if you wanted to. You don't have to use the Henderson-Hasselbalch equation, but you can still do an ice table. You just want to be careful on the ice table that on that initial line, like we talked about, you do have an initial concentration for your sort of conjugate partner. So when we do add acid or base to a buffer, as we talked about, whenever you add volume sort of to volume, the molarity will change. And what that affects is, in certain cases, you do need to do an ice table. And that ice table should be done in moles. So the moles remain the same. The molarity does change. So as we saw when we are adding, either say acid or base to a buffer, you want to do the initial ice table in moles. Once you've completed that initial ice table, it's really good practice to convert everybody back to molarity. And at that point, you would do that by taking the total volume that you had. So in the example of a buffer, that is, how much buffer you started with and how much acid or base you added to the buffer would get you your total volume. And once you convert it back to molarity, which is a really good idea to do, you have really, again, two options, because you will still have usually a buffer left over at that point, and you could go back into the Henderson-Hasselbalch equation to get the pH after you added acid or base. Or again, an alternative to that, you can do a second ice table instead of the Henderson-Hasselbalch. Any questions on buffers, how to do calculations, any of that stuff that we sort of did last time before we pick up on the next big topic here? Okay, so if you do have questions, feel free to ask. We're off to really the next really major sort of topic here, which is titrations. And we're going to talk about some different types of titrations. We're going to talk about how to do the calculations that involve titrations. So let's just talk in general about, what a titration is. You probably have some experience with titrations if you've taken chemistry before. But titrations is essentially when we add a sort of solution of known concentration kind of slowly to a solution of an unknown concentration. And a lot of times we could use something like stoichiometry to figure out the concentration of an acid, maybe the concentration of a base along the way. We typically use a burette, which is this kind of glass guy here. Also has this little kind of open and shut type place there, which is known as stopcock. You open it up, right? The solution drops down. You shut it, it closes. So we typically add like from a burette. A reminder, in case you don't remember, but a burette, when you look at it, actually has 0 up on top there in terms of the volume. So you're obviously exiting the volume on the bottom. So, oftentimes people read burettes wrong. So if you had something in this region where your volume was, that actually would be 1.5, not 2 point something. So you will start at 0, usually 2 decimal places, and it does increase as you go down. But very, very common people read burettes incorrectly. So again, because you're actually dropping from the bottom, you want to make sure that you read it correctly. Other common thing people do with burettes is they fill it to the top and go, that's 50 at the top, and it's not 50, it's 0. Otherwise, you're going to get the wrong values when you sort of read a burette. But anyways, we fill the burette here, for example, with some type of base, perhaps sodium hydroxide. Down in here, we can have some type of acid in our acid-base context here in this type of titration. And typically, we put in some type of indicator into the solution. Indicators, as we'll talk about at the end of this chapter here, basically will change color, and basically indicators work over a specific pH range. So phenolphthalein is probably a most common indicator most people have used before. And something like phenolphthalein, for example, is colorless in acidic solution. It's actually colorless in neutral solution. It turns pink in basic solution. And it actually works, phenolphthalein, about like an 8-ish to 10-ish range in that ballpark. 8 is like kind of no color, then slightly pink, all the way down to, if you've done titrations before, perhaps, you've hit that really dark pink color. And if you've done titrations before, they usually yell at you like, make sure that it is like the barely color of pink that you could see. And we'll talk why that is in this sort of conversation here about titrations in a bit. Why they tell you to stop when it's like barely any pink. You got to put like a piece of paper up there to see the pink color. We'll also talk about here in this sort of part about titrations, also a very common sort of thing that is said a lot when people do titrations. So again, if you've done titrations before or been in a class where people have done titrations, you usually hear people say something like, hey, I just added 1 drop and it went from like no color to super dark pink. And we'll explain why that happens here in just a bit. So that's usually a very common thing that you hear when people do titrations is cool, no color, and all of a sudden dark, super dark pink. And they're like, hey, I just added like 1 drop. I don't get it. And then depending on your teacher, they may tell you, hey, go do that again. And we'll explain why you probably don't need to do that again if that is the indication of what happens. But typically we titrate to what is known as the equivalence point. And the equivalence point is the point where the reaction is complete. And when we reach the equivalence point in an acid-base titration, that is essentially when all the moles of the acid will equal the moles of the base. So in a sort of acid-base titration, exactly at that equivalence point is where you hit the point where if you're adding base, you've added enough moles of base to completely use up all the moles of acid that you have there. Now, the goal is to stop your titration near the equivalence point. And again, that indicator helps you kind of have a visual reference of you've reached the equivalence point and you should probably stop your titration. Not to be confused with another sort of term that sometimes uses titrations, which is endpoint. Endpoint's where you lay up your titration and stop. And a good titration, your endpoint should be pretty much close to your equivalence point. They should be pretty close to each other. And in a case here, this is like phenolphthalein. I think in this example, again, you can see when you get to that equivalence point, it turns this sort of pinkish color. That indicates you should stop the titration. And at that point, if you're just interested in something like concentration, you can use stoichiometry, the mole-to-mole relationship, the balance equation, and figure out the molarity, perhaps, like I said, of your unknown acid, maybe of your base that you're titrating, whatever it may be. But you could do some type of stoichiometry type problem to help you figure out those things. In our relationship here, what we're going to talk about, in addition to sort of that sort of calculation that you've done before in Chem 50, that's sort of figuring out the molarity or maybe the molar mass of an acid, we're going to talk about how to calculate the pH through an entire titration curve. So that is like beginning to end. And when we talk about end here in sort of Chem 51 here, when we're talking about titrations, we're not actually going to be stopping necessarily at the equivalence point. We're going to actually continue the titration past the equivalence point. So what we're going to see here is kind of the whole picture of a titration from sort of beginning to end. And that includes going past the equivalence point. So that's the point where it turns pink and it doesn't stop you. You just keep going and go darker pink, darker pink, darker pink, and go way past the equivalence point. All right, so we're going to talk about, again, like I said, 3 sort of different titrations. And the first type of titration we're going to talk about is a titration of a strong acid and a strong base, or a strong acid with a strong base. So what's happening in this titration was, for example, say that we're taking hydrochloric acid, which is a strong acid, and we're going to react it with sodium hydroxide, which is a strong base. And we should get a little bit of H2O and some sodium chloride as our reaction. Now, for visualization purposes, what is happening in this titration is up in the burette, we have our sodium hydroxide. Down in your beaker, your flask, whatever it may be, we have our HCl. So we're adding base to an acid in this particular titration, is what we're talking about. So this down here is the volume of sodium hydroxide has been added. This is the pH. This is what is known as the titration curve here. And basically a titration curve measures the pH as you continue to add basically base to it. So it continuously measures the pH all the way around. And this is a classic sort of what a titration curve looks like, this sort of S curve that occurs. And we're going to talk about different parts on this particular curve. The first part we're going to talk about is at the start of the titration. Before you add any sodium hydroxide. So basically at the start of this reaction, or this titration, the only thing that you pretty much have in that beaker is HCl. So you're going to start out here. You haven't added any sodium hydroxide yet. Your beaker there is sitting with just the strong acid, which is HCl. That means that if you wanted the pH, we basically have a pH of a strong acid, which means we can go right into the actual pH equation there to figure it out. So in this titration curve, if we wanted to figure out what the opening pH was right about there at that point, we pretty much can just take the concentration of the strong acid, because in this case, this will give you really the H plus concentration because it's a strong acid. You could go right into the pH equation and that will get you the pH of that solution. So now that you have sort of your opening pH, we want to talk about what happens once we actually start the titration. So once we start the titration, anywhere from when we add that first drop to before the equivalence point, we're actually starting the titration. So we're actually starting to drop that sodium hydroxide into the HCl. So let's talk about what happens at that point. What happens at that point is a couple of things. We are going to get that reaction taking place of hydrochloric acid plus sodium hydroxide, making our water and our sodium chloride in this case. So a reaction is taking place. We are also definitely in this case adding volume to volume. So it will require an ice table to be made. And because this reaction has started and we're adding volume, when we do this ice table would have to be done in moles. So it would have to be done in moles here. Again, we talked about adding volume, and that's pretty much everything you do in a titration is just continue to add volume, 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 which means that all throughout your titration, the molarity is constantly changing, but again, the moles are not changing. So the moles are not changing here, and you will need to do this ice table in moles. So I'm going to just make up a number and say that I started with 4 moles of HCl. And again, I just made that number up. So I'm going to say we're going to start this titration with 4 moles of HCl. I am before the equivalence point. That means that before the equivalence point, the amount of sodium hydroxide I've added should be less than 4 moles in my example. So I'm just going to go with 2 moles. Why should it be less than 4 moles? Because the definition of equivalence point is the point where the moles of the acid equals the moles of the base. So since we are not at the equivalence point where that happens, that means that the base is what I'm adding. So I have to have less moles of base than acid. So this is how also you can use your ice table to help you understand where you are in a titration. So in this particular case, our HCl is what we're starting with. This is what we're adding. And whatever you're adding is less moles than what you started with, that means that you are before the equivalence point. Again, because at the equivalence point, those numbers should be the same. Now, because you are before the equivalence point, because you have not added enough sodium hydroxide to use up all of the HCl in this titration, that means that essentially our sodium hydroxide is our limiting reagent. And that means that when we get to the change part, we know that the change would be the amount of sodium hydroxide that we added. Again, because it's going to get all used up, we haven't added enough to use up all of the HCl. That means at this point, I will end up with 2 moles of HCl, nothing here, and 2 moles of my sodium chloride. Question on this ice table. So again, needs to be done in moles because we're obviously adding volume. At this point, because we are before the equivalence point, we know that the sodium hydroxide should get completely used up, and we end up with these 2 things. Now, just like normal, after you do this first ice table in moles, it is super good practice to convert these guys back into molarity. And again, we would do that by using, at this point, our total volume. And in this case, that is how much we started with in the beaker and how much we added from the burette to get to this point. So you want to divide by the total volume. So when you look at these things, what you have left is HCl and you have sodium chloride. So if I wanted to calculate the pH, I could use the, and if you're saying Henderson-Hasselbalch equation, I'll just give you a hint, that is wrong. These are not a buffer here, right? HCl is a strong acid. Sodium chloride is a weak conjugate base. These are not a buffer here. So we really have 2 things. We have sodium chloride, which if you remember from our talk of salts, this guy is neutral, which means he is not going to have any effect on the pH of this solution. Again, sodium being group 1 is neutral. Chloride that came from hydrochloric acid, not going to go through hydrolysis or anything like that. So really what you're left with at this point in the titration is still a strong acid. And that means if you want the pH, you should go into the pH equation to figure it out. So at this point in the titration, anywhere from when you add that first drop all the way up to the equivalence point, you need to do 1 ice table. And really the purpose of this ice table that needs to be done in moles, the purpose of this ice table is to figure out what is your new concentration of your strong acid. And once you get the new concentration of your strong acid, you can then put it into the pH equation and calculate the pH. Any questions up to that point in the titration? And again, that goes from, again, like I said, as soon as you drop that first drop, all the way up to right before the equivalence point, anywhere here in this part of the titration where it's labeled 2. We also see that we are adding base, so we start to see this sort of increase in pH as we're adding sodium hydroxide in this particular example. Any questions up to there? Okay. Now, let's talk about what happens when we get to the equivalence point. So as we approach the equivalence point, as you can see on this graph, the pH is going up, and then usually what you will see is what we see on this graph. There's usually a pretty good leap to the equivalence point, and then afterwards there's another leap in pH after the equivalence point. But this really answers one of those questions that you commonly hear when people do titrations. Like I said earlier, hey, I only added like 1 drop and it went from like no pink color to like this super dark pink color. And that is because as we approach the equivalence point, as you could kind of see here, the equivalence point becomes pretty darn vertical. And the result of that is, although it is vertical here, that means that if my equivalence point is here, I don't have to add a lot of volume because it's going vertical, right? Volume going this way. So we're not adding a lot of volume, but that little bit of volume is enough to leapfrog the pH up pretty high. And how does that affect like your indicator? So as before, phenolphthalein, which is that common indicator that people use, again, something like 8.3 to 10-ish. At the 8.3 area, it's almost colorless. And then again, you get like a tinge of pink to that super dark pink color as you head towards this way. And when you add one drop, although you're not adding a lot of volume here, that one drop is enough to change the pH a lot, which means you potentially could see it being colorless, and that one drop or two drops maybe even is enough to jump the pH to like a pH closer to 10. And what that's going to show you is this super dark color in your flask if you're doing your titration. So if you've ever done that, that is why that happens, that, hey, you're like color comes, color goes, and you just add that one little drop, and all of a sudden it just went super dark pink on you. And again, sometimes people get really tied into a vicious loop of doing titration, especially in Chem 50, because they're like, I've been told I need to get the super lightest color pink that I could get. And mine obviously is not super pink. And the reality is, it won't make that much of a difference if you really did miss the equivalence point there by like a drop or so in terms of the pH, because even if you ended up here in terms of your color, if you go straight down, that's essentially about the same as it would be from your equivalence point. So in terms of the calculation, in the reality, even if you got that dark color, it really didn't make a big difference in the overall result of something like calculating the molarity, because the overall volume would be relatively the same. It wouldn't make a tremendous difference. And that's why, more importantly, when you do titrations, you oftentimes want to make sure that the volumes agree with each other. So the volumes to reach the equivalence point agree with each other, and that usually turns out right. Now, don't get me wrong, if you just open that thing up and you just let it flow like there's no tomorrow, and you weren't really being careful, and you not only added one drop too many, but like a lot of volume too many, and you actually ended up over here, which would have the same color scheme as, say, over here, that would make an effect, obviously, on your overall calculation. But if you were sort of really, really careful and you kind of went drop by drop as you got close to the equivalence point, and again, you just maybe missed it by one drop or two drops, in the grand scheme of things in terms of calculation, it probably wouldn't make a tremendous difference. But again, if you opened it up and just let it flow in and weren't really paying attention and just at some point shut it, you probably could find yourself way too far away from the equivalence point. Any questions on that part of it there? Okay. So this is typically always what we sort of see as we approach the equivalence point. Again, in this type of titration, we're increasing the pH. We typically see that big kind of jump in pH to the equivalence point, and then we typically again see a jump past it after the equivalence point before it starts to sort of level off on the back end. So let's talk about how we can figure out the pH when we reach the equivalence point here in this type of titration. So let's just go back to sort of a calculation here. So we'll call the equivalence point there number 3. And at that third step, at the equivalence point, we would have our reaction happening. So again, we would have our HCl, our sodium hydroxide, our water, and our sodium chloride. All right. So you will need to do an ice table just like before. Again, here we are continuously adding volume. So we need to do this ice table in moles. And again, I'm just going to make up this number. I'm going to again say I'm starting with 4 moles of HCl. Now, because I'm at the equivalence point, that is the point where the moles of the acid should equal the moles of the base. which means I know I should have at this point 4 moles of the base that I am adding. Again, that's basically your definition here of equivalence point, which means you really can't mess it up. There's only one number here, so our change would be -4, which means when we get to equilibrium, we have nothing of this guy, nothing of this guy, and we have 4 moles of this guy. Just like we talked about before, we would want to convert this back into molarity, dividing by the total volume. So again, people often struggle with what is going on, in the titration. Where am I at in the titration? You can use your ice table to help you figure these things out. So again, we see here we have the same number of moles of our acid and base. That tells me I am exactly at the equivalence point. We could also look at our table once we complete it and figure out what we have left. So once we reach equilibrium, we essentially only have sodium chloride left. So we pretty much only have this salt left at this point, sodium chloride. And as we talked about up here, and as we talked about with salts, sodium is a neutral salt. Chloride is also neutral because it comes from a strong acid, which means when we reach the equivalence point in this type of titration, the pH should be 7. You actually don't really need to calculate it. The pH will always be 7 in a titration of a strong acid and a strong base, as we could see right about there, pH is 7 at the equivalence point. So whenever you pretty much do this type of titration of a strong acid with a strong base, the only thing that you will be left with once you reach that equivalence point is essentially water and a neutral salt. And that neutral salt, again, will not go through hydrolysis and will give you a pH of 7. Any questions up to that point there? All right, so in this class, like I said, we actually go past that equivalence point here to get the full sort of look of our titration curve. So once we go past the equivalence point, this is the point where your indicator turns pink and it doesn't stop you. So you just open it up and continue to add. We're going to go past the equivalence point. So anywhere past the equivalence point to the end, we'll call this number 4 here, which is past the equivalence point. Let's talk about how we can figure out the pH at this point in the titration to sort of finish our curve, get our completed curve. So looking at part number 4 there, which would be after the equivalence point. Well, after the equivalence point, we are still doing the same reaction in this example, which is hydrochloric acid, sodium hydroxide. A little bit of water and some sodium chloride. So after the equivalence point, you still need to do an ice table. It still needs to be done in moles. So again, we're going to use our starting amount that we've been using, which is 4 moles. Again, just made up the number. So what we want to think about here is, what does it mean when we go past the equivalence point? Well, we know that once we hit the equivalence point, that is the point where exactly the moles of acid will equal the moles of the base. So essentially, in this case, we've added enough moles of base to use up all of our acid. That means that when we go past the equivalence point, like in my example, you pretty much are opening up your burette, you're dropping in more sodium hydroxide in this case, and you're pretty much just dropping in a bunch of sodium hydroxide, which means that at this point in the titration, the amount of sodium hydroxide, or the base, should be more than what we started with. So I'm just going to use a number of 6 moles here. And again, by looking at this ice table, if you were not sure where you were at, by seeing that what we are adding is more moles than what we started with. That will tell you that you are past the equivalence point. So that's how you know you are past the equivalence point if you're not sure where you're at. And it is super important to understand where you are at in these titrations so that you can do the right type of math. So again, these ice tables, if you do them correctly, can really sort of help you visualize sort of where you are at in that particular titration. So what also happens at this point is, because I am adding way more sodium hydroxide than I need to get to the equivalence point, there's a change that occurs. And what ends up happening is, before our sodium hydroxide was kind of like the limiting reagent. Now, because we're just going right on past the equivalence point, our sodium hydroxide in this example becomes like the excess reagent. And that means that actually our HCl in this case would become like the limiting reagent. What that affects is the change part. The change part here is actually going to be all of the acid is going to get used up because of that. And by the way, you can't have a negative number, so it's always got to be the small number on the change. And that will give us 4 moles on this side. That means when we reach equilibrium, we have used up all of our acid we started with because we are past the equivalence point. We have 2 moles of our sodium hydroxide. We have 4 moles of our sodium chloride. Again, at this point, we want to convert it back to molarity by dividing by the total volume. And again, if you're not sure, you could use your ice table here to help you understand what you have left at this point. So at this point, I have sodium hydroxide and I have sodium chloride. So again, here we want to figure out the pH. Again, here, this is not the way to do it. Yes, this is not the way to do it. These two things are not buffers. They are not related to each other at all. So you definitely should not be using, again, that Henderson-Hasselbalch equation here. And I write it because people always want to use it whenever I have 2 numbers. Seems like a great idea. So let's talk about what we really do have left over. Let's first talk about our good friend sodium chloride, which we have seen the last couple of times. It is still a neutral salt, so it is not going to affect the pH. That means ultimately the only thing that we have left at this point in the titration that could affect the pH is sodium hydroxide. And that is a strong base, which means from that you can get the hydroxide concentration. Once you have the hydroxide concentration, you cannot calculate the pH, but that will get you to the pOH, and then you could get yourself to the pH. So once you go past the equivalence point, it is going to require an ice table. The purpose really of this ice table is to figure out the concentration of the strong base that's left over, the amount of base that you're just dumping in there. And then you can figure out what the pH is from the pOH. Question on that? So on this titration curve, which has this typical S type of situation that's happening here, there's really 4 sort of distinct areas. There's before you start the titration. So again, in this case, what you have is just a strong acid. And because you have not added anything to it, you can go right into the pH equation at that point. Once you start adding sodium hydroxide, or base in this case, all the way up to right at before the equivalence point, it is going to require 1 ice table done in moles. The purpose of that ice table, again, is to figure out the new concentration of your strong base. You then could go into the pH equation and get your pH. At the equivalence point, really, what's going to happen is, because the moles of acid equals the moles of the base, you will be left with just a neutral salt 100% of the time. And because that's neutral, we would expect the pH at the equivalence point to be 7. Heading past the equivalence point, like we just did, requires one ice table, again done in moles. The purpose of this ice table, as we just talked about, is to figure out the concentration of your strong base, which will get you your OH minus concentration, and then get you your POH and your pH. So there's really sort of four distinct areas usually in a titration curve, and those are the four areas. Again, this is specific for this type of titration, a titration between a strong acid and a strong base. So that's an important part of this as well, specifically for this type of titration. That should allow you to calculate the pH anywhere along the titration curve. I ask you to do so, or all the way around it, if I'm really not happy with you guys, I suppose. Please calculate 400 titration points. No, I'm just kidding. But you should be able to really sort of calculate the pH anywhere along the way in this type of titration. So why don't you try one here with maybe some real numbers here. Let's see. Let's do let's say you did a titration of 25 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. What is the pH after 23 milliliters of sodium hydroxide is added? All right, why don't you take a couple of minutes to see what you come up with? I will do it as well since I just made it up. Hope we'll get the same answer. All right, take a couple of minutes here. What is the pH in this titration, just like the one we've been talking about, after you add 23 milliliters of sodium hydroxide? Okay, so let's take a look at it. So we're obviously doing a titration here, so it's very similar to what we've been doing. The setup again is in this case, we have our sodium hydroxide up in our burette, in our beaker that we're dropping into. We would have our HCl. So again, we're adding the sodium hydroxide to the HCl, which obviously means we're going to have a reaction take place. So that is going to be the same one that we've been talking about, which is our HCl and our sodium hydroxide going to make our water and sodium chloride. So we do need to do an ice table. And again, we need to do this ice table in moles. So we need to figure out the moles of each of these things. So the moles of HCl would be our volume converted to liters times our molarity. Liters cancel, and we end up with there 0.0025, looks like 0.0025 moles. So initially here we have 0.0025 moles. We need to do the same thing with our sodium hydroxide. So that's going to be 0.023 times 0.1, going to give us 0.0023 moles, and 0 this guy. Any questions on that so far? So we're just getting our moles using volume and molarity. At this point, again, if you are not sure where you are at in terms of the titration, you know that you are starting with this guy and you're adding this guy. And we can see that the moles that we are adding is less than the moles of what we started with. That means that I know I am before the equivalence point. So again, you could use your ice table and your numbers to help you visualize where you're at while you're doing the calculation here. That also means that at this point in the titration, our sodium hydroxide is limiting. It is less moles. So we're going to use that as the change. So 0.0023 will be our change. Plus 0.0023. That means at equilibrium, we will have 0.0025 minus 0.0023 gets us 0.0002 moles. We have 0 here and 0.0023 moles here. Any questions on the ice table so far? All right, at this point, like we talked about, it is a good idea to convert back into molarity after this first table. So we want to do that by taking our total volume. So in this case, our total volume is our 25 plus 23. That looks like 48 milliliters, right? So what we want to do, obviously, is divide by 0.048 liters. Remember, we need it in liters. And if we do that, we will end up with 0.004167. And on the other end there, we will end up with 0.0479 molar. Now, again, if you're not sure what's going on at this point, you can look at your ice table here, and we see we have sodium chloride left over, and we have sodium hydroxide left over. I'm sorry, not sodium hydroxide, wrong one. HCl left over. Helps if you box the right thing, I suppose. Try that again. There you go. So we have HCl left over, and we have sodium chloride left over. Although they are related to each other, again here, this guy, the sodium chloride, is a neutral salt. So we don't have to really worry about it. So really the only thing that's going to affect the pH is actually our acid here. And again, since this is a strong acid, this will also be our H plus concentration, which means our pH would be minus the log of 0.004167. And that was going to get us pH of 2.38. Question on any of those parts of the titration there, calculation. So let's see if this makes sense. We could maybe see if it makes sense here. We were at 23, which is right between these two numbers, and 2.38 is between those two numbers, so that's good. So we are definitely here before the equivalence point. Any questions on that? Questions on this type of titration? So it's really important to understand where you are in the titration, because if you understand where you are in the titration, you should understand what your answer should be, and you should understand if your answer makes sense or not. And in a lot of cases, you could also understand what you should be doing before you actually do the calculation. So a lot of times it's super helpful because it tells you where you should be going before you start it, instead of just starting in and getting lost halfway between. Any questions on any strong acid, strong base titration? Okay, then let's talk about the next type of titration, which is a weak acid and a strong base titration. So we have our titration curve on the bottom. So this is different than the titration we've been talking about here, in the sense that we are using a weak acid and a strong base. The setup is similar. The setup is, again, in the burette is our sodium hydroxide. In the beaker, the flask, is something like acetic acid, like we have up there. Our acid is here. So again, we're adding our sodium hydroxide to our acetic acid, so our base to our acid. So what we see here is we have an acidic pH. We see still our same sort of S curve happening. We also see, as we approach the equivalence point, just like the last one, we see a jump to the equivalence point, and then we see a jump after the equivalence point. So let's talk about all the different parts here in this type of titration. So starting at step number 1 here, before you add any. So before you add any base at the very start of the titration, the only thing that you have in the flask is a weak acid, which means if you want the pH to this guy, you're going to have to do an ice table. And the ice table would be a Ka type of problem because it's a weak acid. So you would need to do your weak acid. So in this case, something like acetic acid, breaking apart into H plus and acetate in this particular example. This ice table can be done in molarity because you have not added any base yet. So you could do molarity like a normal Ka problem like we did earlier on. These guys would be zeros. These would be minus x's, plus x's. You would bring everybody down. You would go into your Ka expression, solve for x. X, as we could see here from our table, will equal the H plus concentration, and then you could get the pH. So already you can see that this type of titration is different than a strong acid and strong base titration, because here at the beginning, what we're left with, or what we're starting with, is a weak acid. So it does require a different calculation because of the acid that's present. It is, again, a calculation that we've done before. And again, this is a basic Ka type calculation. Any questions on the start of this type of titration? Okay. So once we start rolling in to our titration here, and as soon as we start adding our first drop, again, all the way up to our equivalence point in this region, we are going to get a reaction that's going to occur. So it is, again, going to require you to do a calculation. So at step number 2 in this type of titration, which is before the equivalence point, it again is going to require an ice table. So if we look at our ice table for this example, acetic acid plus some sodium hydroxide, going to get us there. What we got there? We got some water and a little sodium acetate here in this particular case. All right, oops. Now, because we've started the titration and we are adding volume, this ice table again needs to be done in moles. So initially, again, I'm just going to make up the number. We're going to go with 4 moles. And again, we're going to pretend that's how many moles we started with. Now, because I am again before the equivalence point, that should mean that the moles of what I'm adding should be less than what I started with. So I'll use that 2 number again and 0 here. So because we are before the equivalence point, that means our sodium hydroxide is again going to be the limiting reagent. So that's going to be -2, -2, and +2 moles. That means when we reach equilibrium, we will be left with 2 moles, 0, and 2 moles here. Any questions so far? So at this point, what we want to do is convert back into molarity. So like I said before, we want to divide by the total volume to get our molarity. And again here, if you're not sure what's going on, you should look at your ice table. And what we have left here at this point at equilibrium is acetic acid. And we have sodium acetate left over. That is a weak acid and its conjugate base. This is 2 things that are related to each other, and this is also known as a buffer. So we actually have a buffer that is left over at this point, which means if we want to calculate the pH, this is where we could use our Henderson-Hasselbalch equation because it is a buffer situation. And you could get your pH. Alternative to that, you could set up a second ice table. That is the weak acid breaking apart, just like we did when we talked about common ion. And you would take this table, you would take the molarity of these guys, and they would become your initial concentrations on both sides. So you would need a molarity on both sides, -x, +x, +x, molarity -x, x, molarity +x. You would go into your Ka, get your x would equal your H+, your H+ would get you to the same pH as you did here. So again, here you can see this titration a little different than the previous one. when you start this type of titration all the way up until you reach the equivalence point, it will end up being a buffer, and it will end up being an acidic buffer. And that means that you need to minimum do one ice table. Purpose of the ice table is to get the concentration of the weak acid and conjugate base. Then I probably would go into the Henderson-Hasselbalch equation. Or you could do one ice table to get those numbers, followed by a second ice table, and not do the Henderson-Hasselbalch. So everywhere in this titration here, from beginning the titration to before the equivalence point, this is going to end up as a buffer area or a buffer region of the titration. So we got sort of a slow, gradual increase in the pH, and again, before we reach that equivalence point. So again, anywhere in this area there, this mark 2, is going to require what I just said, at least one ice table, always going to end up with a buffer, followed by the Henderson-Hasselbalch equation. Any questions up to that point? All right, so let's talk about what happens when we do reach the equivalence point. So right there at that circle is the equivalence point. We'll call it number 3. So let's see what happens when we do get to that equivalence point. So in this type of titration at the equivalence point, we're still going to have our reaction, which again in this case is our acetic acid, which is our weak acid, plus our sodium hydroxide, which is our strong base. Going to give us some water and sodium nitrate. So at the equivalence point, if we start with our normal 4 moles that I made up, because we are at the equivalence point, that means that these two guys should be equal to each other, and we should have the same number here. Again, that's pretty much your definition of equivalence point. We will have 0 here. Again, here you can't really pick the wrong number. It is 4 in my example as the change. That means when we reach equilibrium, 0, 0, and 4 moles, we again want to convert back to molarity using our total volume. So at this point, what we have left is our salt, which is sodium acetate. And you got to think, will this affect the pH? And the answer is, as we talked about earlier, yes, it will. So sodium acetate is basically the sodium ion, which is a neutral ion. So the sodium part will not affect the pH. But the acetate part will, because the acetate part came from this guy, which is acetic acid. Acetic acid is a weak acid, which means the acetate part of sodium acetate will continue on and react. And as we talked about, since it's a salt, it's going to react with our water that's present, which means once you're done with this ice table, you then need to have a second ice table. And that second ice table is the hydrolysis reaction, in this particular example, of acetate plus water. So what is acetate going to do? Well, since it came from a weak acid, it is probably like a conjugate base, which means it's going to act as a base in this case, and that means it's going to accept the H+. When it accepts the H+, it will form where it came from, like we talked about, which is acetic acid, and it will form hydroxide here. So before I even do the calculation, just from writing this equation correctly, which is why it's really important to be able to do this, I see I have OH minus. And this tells me several things that we talked about earlier on in this chapter. once I see that OH minus, I know when I do calculate my pH, it should be basic. I also know when I see the OH minus that in my calculations, I need a KB value. And I say that because probably in this case, you would be given the Ka value for your acetic acid. So again, here we'll need to use that thing that we saw earlier, Kw equals Ka times Kb. So again, all these things are tying together here. So we got to use that to get the right value. So we will do a nice table here. Just like before, we're going to take our equilibrium value. This becomes our initial value. So from above. So the molarity value from above becomes our initial value here. These are going to be zeros. This is going to be minus x plus x plus x. It's going to give you your molarity minus x, x, and x. As we talked about, this needs to go into a Kb value, an expression. You will solve for x. X in this case does not equal the H plus concentration. It equals the hydroxide concentration, which means you got to go POH and then off to pH in that order. So definitely a lot different than the strong acid, strong base titration, where you reach the equivalence point and you pretty much write 7. Here you do not. You actually will expect a basic pH, because when you reach the equivalence point in this type of titration, you are going to be generating a salt that will go through hydrolysis. And when it goes through hydrolysis, it will produce hydroxide, giving you that basic pH at that point. And that is what we see when we look at this titration curve. We see that when we reach our equivalence point in that titration, something like 8.72, which is basic. This is also why you use something like phenolphthalein for this type of titration. If you've ever done a vinegar and sodium hydroxide titration, because the equivalence point is around 8.7, phenolphthalein works about 8.3, and it starts to see color around there, and that's why they yell at you, hey, just the lightest color pink, because that should put you right around the equivalence point. Question on what to do at the equivalence point in this type of titration. All right. Then, of course, we will continue on past the equivalence point. So again, past the equivalence point to sort of our end in our titration, again, we still see that kind of jump in pH to the equivalence point, and then we typically will see that jump after the equivalence point before it starts to sort of level out at some point. And that is part number 4 of this titration curve. Let's take a look at that. So 4 would be after the equivalence point. And after the equivalence point here, we are again just dumping a lot of sodium hydroxide in this example in there. And again, we will need a ice table. So we're again going to do this in moles. So we'll start with our 4 moles of acetic acid. We're adding our sodium hydroxide here. And in this case, because we are again past the equivalence point, this means that what we're adding should be more moles than what we started with. So again, I'll use that 6 as an example here. And we'll go 7. So the same thing happens because we're just constantly adding our sodium hydroxide down. It becomes kind of the excess reagent. And we get a change that occurs, which is the acetic acid becomes the limiting reagent. So this guy becomes kind of the limiting reagent in this case. And that is going to be our change that occurs. Again, you can't have a negative concentration, so keep that in mind. That means when we reach equilibrium, we got nothing there. We got like 2 moles there, got 4 moles there. Again, here we're going to convert back to molarity by dividing by the total volume of our titration. And we want to figure out the pH. So we want to think about what we got left over here. We got sodium hydroxide and we have some sodium acetate. And again, here, these two things are not a buffer. So you should not use the Henderson-Hasselbalch equation. So will the sodium acetate affect the pH? The answer is yes. We just talked about it a second ago. But in addition to that, we have sodium hydroxide, which is a strong base. This guy's also going to act as a base. Now, in comparison to these two, the sodium hydroxide is a much stronger base. Pretty much it just needs to go into the solution to generate the OH minus. The sodium acetate's got to go find water, do a little reaction to generate the hydroxide or the OH minus. And what that means is at this point in the titration, even though the sodium acetate is contributing to the pH, it's not contributing a lot. And we typically will ignore its contribution at this point because sodium hydroxide is a much stronger base than sodium acetate. And what that means is at this point, that will give you your hydroxide concentration, which will allow you to calculate the pOH and then to the pH in this particular case. And again, this is because sodium hydroxide is a much stronger base than sodium acetate, and it's going to be a major contributor really to the pH. So past the equivalence point in this type of titration, you need to do one ice table. Purpose of the ice table is to figure out how much strong base you have left over so you can then calculate the pOH and then to the pH. Any questions on that part of it there? So you can see in this titration, although it may look very similar to the titration we were just talking about, there is really 4 distinct places to do these calculations or parts of it. The good news is we've done all these calculations before. The bad news is people have a tremendously hard time figuring out what calculation you should do. And that's why it's important to know where you are in that titration, because even before you pick up the pen to do the calculation, you should kind of know what type of problem you should be doing. Should I be doing a buffer problem? Should I be doing a hydrolysis problem? Should I, be just doing a figure out the strong acid or strong base type problem? So it allows you, if you sort of have a good understanding of what's going on, before you even do the calculation, try to know exactly where you're going. Again, too many people rush right into the calculation, don't really think about it, what's going on in the problem, and they just kind of get lost. Or they just go with, I got 2 numbers, I'm just going to put it into like the Henderson-Hasselbalch equation. Any questions on that there? So why don't you try one here? Let's go with, let's see here. Let's say we did a titration of acetic acid, 25 milliliters, also 0.1 molar with 0.1 molar sodium hydroxide. What is the pH after, I don't know. Let's go with, let's do 27.5 milliliters of sodium hydroxide has been added. All right, take a couple minutes here. I will as well, since I just made it up. We'll hopefully hit the right answer together. By the way, the Ka value for this guy, in case you need it, 1.8 times 10 to the minus 5. Okay, I tell you what, since it's sort of the end here, why don't we stop? And I think we're going to lecture a little bit on this stuff here in lab at 11:30. So continue working on this one. We'll pick it up at 11:30 since we're sort of in the middle-ish here of this topic. And we might do a little bit more lecturing on this stuff just to kind of finish up the titration sort of topic. All right, so we'll stop for now to take a break, and we'll see everybody at 11:30 in lab. Make sure you put here if you haven't done so already.